Hey there, everybody. If you are watching this, it is sometime between uh, February 23rd and February 26th. During this time, if you are virtual, you will be working on this lab. So again, this is only for virtual students, and you'll be working on this both of your virtual days through this week. This lab is the Habitable Zones Lab. Where can planets be relative to a star where we could survive on an Earth-like planet? Something that that's known as the Goldilocks zone. For those of you that are familiar with like Goldilocks and the Three Bears, there's the porridge that's too hot, too cold, or just right. There's the bed that's too hard, too soft, or just right. Um, if we're looking out in space and we're looking for a place to be, we need to find an area of space surrounding a star that is habitable. Not too hot, not too cold, but just right. You'll learn exactly what makes this just right and how that changes with every star as this goes on, but also, even more specifically, what needs to be just right. Why does the temperature need to be proper? What is this reliant upon? A lot of this is captured here in the pre-lab. This pre-lab here is the very first page, and it's pretty dang short. There's 4 questions. So at this time, go ahead and pause this video and follow the instructions in the pre-lab and resume once you are done with the pre-lab. Okay, I'm going to assume at this point that you have paused already and you have finished questions 1 through 4. Questions 1 and 2 pertaining to research, 3 and 4 pertaining to the reading portion right here. I want to make a very specific announcement here that you can, if you are using a home computer and you're comfortable with it and your parents are okay with it, you can download the following simulator yourself. However, this simulator, I'm going to say like 99% certain it's not going to work on a school-owned computer, especially the Chromebooks, because this requires you to download more stuff and work outside of Google. So odds are this will not function. So if you are not planning to download or you don't want to download, well, I'm going to be showing you the simulator as we go forward. So every next portion of the lab here is going to deal with everything, deal with the simulator that I'm going to be showing to you. So circumstellar zones. We're going to begin with the sun being displayed as it was when it formed and a terrestrial planet at the position of the Earth. We can change the position of that planet relative to the sun by moving it around. So what we're going to want to pay attention to is how this looks in our simulator. Here we are. You will see right here that we have the sun very early in its lifespan, and we have the Earth at its current orbit at the time of our solar system's formation. So let's just take a second to familiarize ourselves with the simulator itself. We'll see the stars in the center here. It shows us, just for relative scale, the orbital distance of planets like Mercury, Venus, Earth, and Mars. And we've got our planet right here that we can move around. And you'll notice that if I move it inside the habitable zone, we're too close, we burn up, we got a desert-like planet. If I move it too far, it's less tan and more of a light color, kind of a white color, icy. There's that comparison just to show you. So we're either roasting the planet or it's too cold. So this habitable zone, the Goldilocks zone, is where the temperatures are just right for liquid water, as you learned in the pre-lab. So I've got the Earth back where it needs to be, just representing where it is at the moment. So let's just look at some of the data down here. Star and planet settings and properties. We're not really going to be changing this too much, but you can change the star and the system to represent different planets and exoplanets. Or I guess I shouldn't say planets and exoplanets, but different stars and their relative exoplanets. This stuff is a little bit janky, and it's not going to really get us the information that's super useful. If you're interested, you can always let me know or pull up the simulator yourself and give it a try. But I'll just show you real quick. Like, we shrink the star down. You'll notice that Gliese 581, very small star in the center of this system, and Mercury, it all sits within the orbit of Mercury, which is pretty crazy. But we're going to return back to the initial state here and just talk about our sun. So in the settings and properties, we can see the star mass. Right now, it is at 1 mass, specifically 1 mass of the sun. You'll remember in an earlier unit that you can denote that by putting M and then a circle with a dot next to it, meaning 1 solar mass. So right now, our sun is 1 sun large. We can increase this and make it 4 suns large or half a sun large or whatever. But again, we're going to start just by looking at our sun. We can then change the planet distance, which we can change by, typing in numbers, or we can take the planet itself and yank it around, and you'll notice that distance changes. The luminosity of the star is provided right here relative to that of the sun. The luminosity at this point in time is 0.739 luminosities of a sun. 0.739 of a sun, you might be thinking, like, what? Wait, isn't the sun 1 sun bright? Yes, it is. The thing is, remember that this is representing the sun right when it formed. Down here at the bottom, you'll see the timeline and simulation controls, where we can see time since the star system formation, 0 million years. 0 million years. So this is right when the sun formed. We can take this slider and move it around, and we'll see, like, if we get up to 4.6 billion years, or about 4.6 billion years, the age of the sun as it is right now, then we get the luminosity to our modern levels. But we'll play with that time slider more as we move forward. For now, let's refocus right here. Luminosity at the early point of the sun's formation is about 74% of what it is now. The surface temperature of the star, our sun, is 5,700 Kelvin. And then the radius of the sun is about 89% that of the sun. Now let's get to the lab stuff. Now that we know how this device works, we can start answering some of these questions. So, question 1 says to drag the planet to the inner boundary of the circumhabitable zone and note the distance from the sun. Then drag it to the outer boundary and note the value. We're going to take the difference of these two figures to calculate the width of that of the sun's circumhabitable zone. So I gotta switch screens. Here we go. Let's drag it to the inner edge and let's notice how far a planet can be from the sun to be right on the front edge of the CHZ. So I'll move it right here and I'm just going to wait. Oh, there it died. Let's get it as close as we can. And it's just barely alive here. So there's our initial planet distance. You can be, at least early on in the solar system, you could be 81.7% or 0.817 AUs from the sun and still be in the habitable zone. Let's check the outer edge. Make sure you recorded that number in the initial table. And we'll see how far away from the star we can go before we die. Oh, and right about there. Looks like about 1.17 AUs. So we'll want to make sure we record that information here. What was it? 0.83, 1.17. Let me double check that real quick. Looks about 0.82-ish. Let me fix that up right here. Boom. Okay. Now it's asking for the width of the CHZ. How wide is the Goldilocks zone? Well, the closest you can be is 0.82 AUs. The furthest you can be is 1.17. So we run that math. 1.17 minus 0.82. We get about 0.35 of an AU. That's how wide that is. The next portion of this lab, and this is where it's going to become a little bit more time consuming, we're going to want to compare a whole bunch of information like that's not our sun. Yeah, our sun's really easy to work with. We can make these measurements, but not every star is like the sun. So what's the habitable zone like for a star that's only 30% the mass of the sun, or 70%, or 4 times the mass of the sun? What you're going to need to do here is you're going to have to follow along. You'll probably have to pause the video several times. And as you do, make sure that you're recording all of the information here. If we go to 30% the mass of the sun, how luminous is that star? Remember, that information can be found right here, luminosity. You'll take the luminosity, and then you'll just recreate what we did up here. What's the inner boundary of the CHZ? What's the outer boundary? And then, therefore, how big is the CHZ? So at this point, I'm going to be pretty quiet, and I'm just going to be dragging the slider around so that you can gather this data. Pause as much as you need to gather that information. You'll have to crunch the numbers and use a calculator for the width of the CHZ in some of these cases. But here we go. We'll start with 0.3, and we'll go up to 0.7 and 1. Well, very clearly, you'll notice an intuitive observation we can make here. Think about it. I just changed this to 0.3, 30% the mass of the sun, and the CHZ is way over here, way closer than that of Earth's orbit. Why would that be? Now that you've had some time to deeply reflect on the question that I asked you, let's actually go into the data table here. And we're going to move this closer, and we'll go to the inner boundary. About right there. We'll go to the outer boundary. Right there. And make sure you grab that luminosity number as well. Okay, we're going to switch up to the next one, 0.7. So we're at 0.7 solar masses. Here's the inner boundary. Here's the outer boundary. I believe the next ones, let's see, we want 124, 815. Okay. For 1, we already have that data. You can take that from the section above. Now we'll move on. I'll do that just in case you want to follow. Here we go. Moving on to 2 solar masses. You can see our star even increased in size a little bit right there. This arrow says, you got to move this way, buddy, if you want to be in the habitable zone. Woo! Okay, look at that. Now we're out to like the orbit of Jupiter with 2 solar masses. You'd have to be this far away to have water or liquid water on that planet. Inner boundary. Outer boundary. Going to move up to 4 solar masses. Here's the inner boundary. Outer boundary. Going up to 8 now. We're at 8 solar masses. Here's that inner boundary. Here's that outer boundary. Cool. And then I think the last one was what, 15? 15, all right. Ooh. All right, we're way out here now, well beyond Pluto. We're into those Kuiper Belt objects now. Inner boundary. And outer boundary. Very nice. So, at this point, we should have this table completely filled out based upon what we saw before. And we're ready to answer questions 3 and 4. Go ahead and pause and answer those questions. Questions 3 and 4. Now that you've answered questions 3 and 4, We are getting ready to move on to the final portion of the lab. However, we're going to save this for day 2. So you're going to want to go ahead and stop here and prepare to, you can finish up any loose ends, maybe work on that Mars write-up if you're not done with it. And yeah, so you'll want to resume the video the next day, about right here. But for now, you're done for the day, and resume at this timestamp tomorrow. Or not tomorrow, but your next time you're virtual. And we're back. So, you're back to day 2 of your Circumstellar Habitable Zone Lab, your CHZ Lab, and we are now looking at the time aspect of the chart. Some of the reflections that you may remember from the previous time is that we were noticing that these boundaries change significantly as the star's mass changes. Of course, you've responded to that in questions 3 and 4, so I don't want to provide too many spoilers for those of you that are working ahead or cheating. No cheating. You'll notice that this varied substantially. And you might be thinking, well, the width of the CHZ, well, doesn't that mean there's more room for planets? Doesn't that mean there's more room for liquid water if that's a bigger CHZ? Absolutely. That's totally true. But one thing that we haven't considered so far is time. And that's where this comes in. So we're looking at the evolution of star systems over time, and we're going to investigate how that affects the CHZ. We'll focus exclusively on stellar evolution and assume that planets remain in their orbits indefinitely. So just like the Earth has been where it is in space for about 4.5 billion years. We're going to assume that these planets stay where they are. But many researchers do believe that planets migrate due to gravitational interactions, but we're not going to show that in our simulator. We're going to assume that these things stay ballpark. They don't move in and out very much. So let's move on to the simulator. This is telling us about 3 sections of our simulator that we're going to have to pay attention to. So let's switch over here. We can see up top here, let me switch this back to the sun. We're looking at the sun and the Earth, and you'll notice that right now, how long has it been since the star formed? 0 million years. So we can change that with our slider. We can either hit the run option to see how that changes through time, or what we're more likely to do here is we're just going to grab this slider and we're going to move this around to make more precise measurements. But here we are with the Earth and the Sun at their earliest stage, 0 million years since formation. So this is the very initial Sun. This is the Earth right when it formed. But then we can move this forward to like 4.6 billion years, about where we are now. You'll notice that our units change. Rather than being in the MY, millions, we are now in the giga years, which means billions of years. So 4.6 billion years is where we are now. Notice that some of these data points change as we do that. The mass of the star stays the same. We have all the same amount of stuff. But you'll notice the surface temperature changes, the radius changes, and the luminosity changes. If we have a change in radius, temperature, and luminosity, of course, that's going to make certain sections of space toastier than others. You can even tell, if you look closely here, I'll really ramp this up. Look at the star as I move this slider. The star will straight up change in size. And as a result, you'd imagine that temperatures are going to change throughout space. So the 3 functions of our timeline are: we can change the time up here, we can see what temperatures are looking like down here, and then also in the very bottom, it shows us the amount of time at which we are in the habitable zone. If you look at this central bar here, this central bar has this line. If you're in the white section, that means it's just right. Blue would be too cold. Red would be too hot. So there's a span of time here where we're in the white, we're in the clear, we're in a perfect temperature situation. But right when we get to the end of this blue bar at the bottom, right when we get to the end of that, oh boy, you can look back up at the simulator and tell our planet is toast. If our planet is toast, that is the edge of the amount of time that the planet can stay in that CHZ, because now the star's heated up that same section of space too much, and we got a problem. So let's see our questions. We're going to configure this simulator to the Earth. It's our sun, 1 solar mass, distance of 1 AU, and we're going to move it to 4.6 billion years. And then we want to figure out, well, how much longer I hate this part of the lab, but I simultaneously love it just because it's so interesting. Let's go to 4.6 billion years. This is where we are in Earth's history. We're at 4.6 giga-years in Earth's history. This is us today. How much time do we have left in the circumhabitable zone? How long until Earth is no longer able to sustain liquid water? Well, if you look at our blue bar down here, oof, we only got this little chunk left here. Let's see how much time is left. You're going to have to do a little bit of math. We start at 4.6, and then we get to here. Make sure you record the number that we have here. What date are we currently at? We were at 4.6, but now we're at what number? When you answer the question, make sure that you do the math here. We start at 4.6 giga-years. We end at some number of giga-years listed here. Subtract the 2. Oh, wait. Yeah, subtract the 2, and you'll get a value. For question number 6, we're going to consider what percent of Earth's lifetime is remaining. You're going to have to take your answer to number 5 and divide it by the Earth's current lifespan of 4.6. Given how long we've been around, about how much longer in a percent do we have left compared to how long we've been here before? Okay, so pause if you need to, if you're not ready for this, but you should have questions 5 and 6 answered by running those calculations and using the information from the simulator. Now we're going to look at question 7. What is the total lifetime of the sun up to the point it becomes a white dwarf? So if we go to the simulator, you will see that we're only about halfway through this lifespan. You'll see that the white dwarf is all the way over here. So we're toast on Earth long before the sun is a white dwarf. So now let's see, how long do we have until the sun is a white dwarf? Let's move our slider. And we're about right there. Hold on. There we go. Now the sun is a white dwarf. So what time do we have below? Make sure you record that and get that ready. That answers question number 7. But now, this is where it gets even more interesting. What happens to the Earth at the time in the simulator when it becomes a white dwarf? More specifically, I'm asking you, why does this happen? You're going to need to talk about the state and condition of the planet and its position in space. You'll be able to best answer this question by thinking back to Unit 4. In Unit 4, we talked about how stars change through time. So I'm going to let the simulator play through. You can rewind and fast forward a couple times, but let's see what happens. So let's watch what happens when the sun becomes a white dwarf. Oh, that's way too fast. So you're going to want to watch a few things. You're going to want to watch the planet itself. You're going to want to watch the star. You might even want to watch the habitable zone a little bit. But watch this back a few times so that you can make some cool observations as it pertains to this question. Slow it down a little bit and we'll do it again. Big oof, right? Let's watch it back one more time and I'll put it back at the interesting parts right here. Make sure you're observing, make sure you're not only watching the star, but you're watching the Earth, and make sure you record any and all of your observations. Pretty crazy. Okay. So, what happens to the Earth at this time in the simulator when it becomes a white dwarf? Why does this happen? And specifically reference the state and condition of the planet. Okay. At this point, you should be finished with question 8. If you need to pause to make sure that that's happened, please do, but finish question 8. One thing I want to point out here, as we look back, is the Hertzsprung-Russell diagram is displayed right here, the HR diagram for star classification. Watch what happens to the sun's position on the HR diagram as it changes through time. It migrates into that red giant stage, and then we end up down here with the white dwarfs. Pretty crazy. Okay. Question 9. We know that life appeared on Earth early in its history, but complex life did not evolve or appear until several billion years later. If life on other planets takes a similar amount of time to evolve, we should evaluate how long a planet sits in its CHZ. This will help determine the likelihood of complex life being present elsewhere in the universe. To make this determination, we're going to set the timeline cursor to 0, and then we're going to drag the planet in the diagram so it just sits on the outer edge of the CHZ. Then we're going to run the simulator. So, we're going to do this with 3 different types of stars. A 0.3 solar masses, a 1 solar mass, and then a 2 solar mass. We're going to put it in a position where it's going to stay in the CHZ for as long as possible, okay? We know that the star is going to expand. If it's going to expand, we want to give ourselves as much room as possible. We want to give ourselves as much time as possible. So if we've got our CHZ right here, notice what happens over time. As I advance time forwards, watch the CHZ. That migrates outwards because that star starts putting out more energy. So by putting it right at the fringe here, we are giving ourselves as much time as possible. The CHZ is allowed to go over the planet if it stays in a stationary orbit. So remember, what you need to mark here is how long the planet will stay in the CHZ. We'll also need to mark, well, how far is that planet at that point? You'll notice in this case, I've already got it set right on that fringe. So the initial planet distance, that outer fringe, is 0.157, already listed for you. But now let's see how long it stays in the CHZ. We can look down here. We can see that our blue section, our Goldilocks time, exists until about right up to here. So let's gather some time, or select that time out of there. And it looks like about right there. Oh, that was a little far. About right there. How long did this planet stay in the CHZ? You'll want to remember it was there to begin with, but where are we now? That is the total amount of time that it spent in the CHZ. But that is for a 1 or a 0.3 solar mass star. Make sure you record this number here in the time here in the table. Now let's look at one that's like the Earth or like the Sun. We want to give it as much time in the CHZ as possible, so we're going to move it to the outer edge. And we're sitting about right there. About right here. Oh, there we go. Note the planet distance from the star in AUs. And now let's see how long a planet could stay in the CHZ for a 1 solar mass star. Record your answer. Remember, this was in the CHZ from 0 million or billion years ago until now. So gather that timeline. And now let's look at it for, what was this last one, a 2? 2 solar mass. Okay. Well, we got some work to do. We're going to have to migrate this out here so it's at least in a good starting point. I'm going to put it out here just beyond the orbit of Jupiter, about right. About right. About right. Come on, move. About right there. What is the initial planet distance? And when will it lose its habitability? We'll trace our simulator out. We watch that CHZ migrate outwards and outwards and outwards and outwards, and then we get a drop about right here. How long did it spend in the CHZ? Okay, your data table should be complete at this point. You should have your times, you should have your initial planet distances. And now, I do want to step back to the simulator for just a second. You'll notice what happens here. It moves inside and out of the habitable zone for a brief amount of time here. And you can see that with this temperature spike right here in the center. If we get these larger masses, they go through slightly different behaviors than that of our sun. Because it's kind of pulsating, it's starting to enter like a variable star state. It's going to release a lot of energy, putting us outside the habitable zone, but then it's going to settle down, put us back inside, and then eventually it's too bad. It's not coming back. Pretty interesting. Okay. Question 10 is one of my favorites, or probably my favorite in this entire lab, because this is going to really set the stage for what we talk about next week, the potential for life to evolve in other places. It took approximately 4 billion years for complex life to appear on Earth. In which of the systems above, meaning of which stars, could that be possible? If it takes 4 billion years for all complex life to evolve, similar to it does on Earth, what can you conclude about a star's mass and the likelihood of complex life? We need to reflect on this lab in general in question number 10. I'm going to assume now that you have finished question number 10, and as a result, I just want you to think about this lab as a whole. Take a moment of honest reflection and just think about stars and the CHZ, the Goldilocks zone, not only in the context of space, but in the context of time. Where is the CHZ, and how does that change depending on the star and its various characteristics? How does the CHZ change if the star is bigger? How does it change if it's smaller? How long will we, as Earthlings, remain in the CHZ? Then we start to tie in that time. Sure, stars can be this big, stars can be this small, the CHZ can be this wide. But how long will that CHZ remain in place? How long will it stay in a reasonable section of space containing a planet? That is highly dependent on its mass. And that's where we reflect right here. So at this point, your lab should be totally complete and you are ready to submit. This needs to be done by Monday, March 1st, because we are moving on to the fanciest of fancy, something that everybody loves to talk about, that is the Drake equation. Now that we understand how life can evolve to some degree, like the best of our ability right now, and we understand where life can be in space and in time through this lab, we're actually going to calculate the likelihood of life elsewhere in the universe. Pretty sweet stuff. Have this completed by Monday, and we're ready to roll forward. I will see you then.